Hi, this is Ron, and welcome to the webcast. Today's topic is advanced calculations in Calc Manager. If you would like to email me, there's my email address. I'm always interested in hearing from Essbase people, particularly about topics such as calculations and design. So please feel free to email me. So today's objective is to show you how to automate creation of business rules and calc scripts using custom-defined templates. This is a Kscope 15 encore session, so it's a repeat of a session that I did at the most recent Kscope. It's also an extension of a previous ODTUG webcast that I did back in January. That webcast in January here's the URL, and that webcast has a lot more detailed keystrokes. So if you're brand new to CDTs, that might be something good to check out. This session focuses on extending the design to a driver-based forecasting or driver-based budgeting calculation, and it uses a simple rolling forecast as an example. Of course, you can do much more complicated calculations as well, but we're going to try to keep it somewhat simple. When I first started trying to learn custom-defined templates, it took me quite a while to wrap my head around it. So I wanted to try to develop a conceptual framework that makes this easier to think about. And we're also going to address a couple of questions that came up during the Kscope presentation, one of which is using Calc Manager to create a simple ASO calculation. And also there's a trick with variables that someone asked about, so I'll try to address that as well. So what are CDTs, or what are custom-defined templates anyway? Think about two different types of users. The business rule designer is the person that's writing a specific script for a specific outline. So that's going to have specific dimension names, specific member names, etc. Think about the CDT designer as a second type of user. That's the person who's writing a generic script structure that could be customized to work on several different outlines or many outlines. So CDTs are like wizards, and you execute them during rule development. They're executed by the business rule designer. When the CDT is executed, the business rule designer is prompted for a series of responses that make that generic script structure work the way you want it to in the specific outline. CDTs are created by the CDT designer. They may or may not be the same person as the rule designer. So the CDT designer is going to drag in various components to create the script structure. The most important components are probably formulas, scripts, member ranges, and conditions, but there's several other components as well. The CDT designer creates design time prompts, DTPs, and those prompt the business rule designer to answer a series of questions. The CDT designer also organizes those prompts into steps. Steps are like the pages in the wizard that the business rule designer sees. The CDT prompts are the questions on those wizard pages. So let's think about the conceptual framework. If you've written very many calc scripts, you know they frequently follow certain patterns. For example, I used to teach a lot of boot camps, and in the boot camp, they referred to the common architecture, and it included the baseline fix and a normalization section and a main roll-up section and the back calc section and a couple of other sections, but those are the real meat of it. And so if you've been to boot camp, you've heard of those things. So this is evidence that scripts follow predictable patterns. Now, of course, not all scripts follow those patterns. Different scripts do different things, but there is a lot of commonality. So what we want to do is we want to identify the static elements that are shared across many applications, and we want to identify the custom elements that are going to change from application to application. We want to create script components for the static elements, and we want to parameterize the customized elements. For the customized elements, we're going to create two different kinds of prompts. We'll create design time prompts for the rule designer, and those will allow the rule designer to customize the script, for example, for a particular outline, particular dimension names, particular member names, etc. We'll create runtime prompts for end-user customizations. Now, you're probably familiar with runtime prompts already because they've been around in planning and Hyperion business rules for a long time. Design time prompts are new with custom-defined templates. So ask yourself, what are the static patterns in the code, such as baseline fixes or mathematical logic? In our example, it'll be a simple percentage growth calculation. What's customized, such as dimension names, member names, and slices. For example, here, is our accounts dimension named accounts, or is it named measures? What is our time dimension named? Which members do we want to apply the percentage growth logic to? What measure are we going to forecast? Are we going to forecast sales? Are we going to forecast units? Are we going to forecast something else? Should the logic be applied to forecast? In this case, of course, it's a forecast. Or should it be applied to history, some other type of calc that's going to be done on our actuals? And what business units should this apply to? So one predictable pattern has to do with what types of dimensions we have. Depending on the purpose of the application, the dimensions can fall into a set of predictable types. So here's three different applications. Let's categorize the dimension types so we can better understand what to do with them. You're all familiar with the accounts dimension property and the time dimension property. This idea is just an extension of that. So starting very simple with sample basic, we have an account dimension, we have a time dimension. In this case, our time dimension is called year total. Let's call the scenario dimension a data type dimension. And let's call products and markets business units dimensions. So that's our classification for sample basic. Some of that is standard dimension properties, and some of it is new with my conceptual framework. Planning is a little more complicated, and custom-defined templates actually recognize or have a type for each of the planning required dimensions. In this case, we've got an accounts dimension. We've got two time-related dimensions. Of course, only one of those can have the time property, but we've got a periods and a year dimension. We have, in planning, we've got 2 data type dimensions, scenario and version. As far as required dimensions go, we've got 1 required business unit dimension, but of course we can add as many custom dimensions as we want, but we're going to keep it relatively simple. Now, in the driver-based budgeting example, I've added 1 more dimension. That's the view dimension. Some people call this an analytics dimension. It's generally a dimension with 1 stored member and then a lot of dynamic calcs for things like year-to-date and quarter-to-date and other types of transformations like thousands or % growth. Now, I associate the view dimension with driver-based budgeting example because I like to put my drivers on that dimension as an additional stored member, and we'll see that this is a very simple, elegant design that is very low maintenance. We'll see examples of that in a minute. So here's a common bit of code. Now, this is just a simple % forecast. It's there's a lot of new functionality in the newer calc functions in the most recent versions of Essbase. In particular, X-range, which has actually been around for a few years, makes this a lot easier. X-range was originally only what X-range does is it takes essentially your periods dimension and your year dimension, and it makes 1 big long virtual dimension out of them, so that you don't need to do this kind of MD shift stuff. X-range was only worked in about 5 or 6 functions previously, but now it works in like 20 or 30. So many more of the functions are easier. But MD shift was the common way to do these types of calculations for many years. So this calculation just addresses the fact that in January we need to look back to previous December to find the previous value to apply the growth rate to. It's moderately complicated. It's not really difficult once you understand it. But there's a lot of parameters. There's some tricky stuff like the optional parameters that cause the double commas here. You've got to remember which order the parameters come in. So it would be nice if we didn't have to remember all this if we wanted to deploy it to different outlines. And it would also be nice if we could hand over a template that could be used by people who didn't understand something like MD shift. So think about your own outlines. Would this code work? What if your years dimension and your periods dimension were different names? What if you have a different fiscal year? So it's not going to be January where you need to look back. Now we could look at your outline and make a few changes, and then this code would probably work. But you'd have to make those changes differently every time you deployed it against a different outline. So those are design time customizations because the rule designer does them, and they do them once, and then you can deploy the code to a specific database or to a specific outline. Looking at the nature of these customizations, it's almost certain that the user will determine the growth %, so that'll be done at runtime. You could also let the user decide which accounts to forecast. So we're going to put this into a custom-defined template, and that's going to make it easier to deploy this. We want to think about what choices we want the end user to make. In this case, the end user is going to pick the measure or measures to forecast. They're going to pick the % to apply. Those are going to be runtime prompts. And the rule designer is going to make a different set of choices, and those are going to be choices that are generally outline-based choices, like identify the year dimension, identify the period dimension. and we'll see we'll make it a little more complicated than that. So this code is a good start, but it's not going to be enough for the whole calculation. We're going to need to add some fixes. In this example, you see in the red, we've got 3 separate layers of fixes, and that's just style to organize them. They don't have to be in the 3 separate fixes. The outer fix, I'm going to call that the forecast slice. So that identifies the years that are going to be forecasted, and it identifies the scenario and version members that are going to be forecasted. Fix 2 is what I'm calling the business unit slice. In this case, I'm identifying just the level 0 business units from the entity, the channel, and the products dimension. Of course, that could be something else. Slice 3 is what I'm calling the stored data types fix. And that's kind of a techie slice that identifies the base member from my view dimension, because that's going to be a stored member where most of my input is, and the HSP input value member if this is a planning application. And notice the forecast slice and the business unit slice are going to be runtime prompts, so the user is going to be prompted for those when the script is run, and the stored data type slice is a design time prompt, and that's going to be prompted when the business rule designer executes the custom defined template. Okay, pause for a moment to look at what I call some of Ron's simple stupid rules, because we're going to get into some design thinking, and we need to think back to the way Essbase behaves to come up with a good design. So, first, the iron rule of multidimensional databases. Every number lives in a cell or an intersection. Every cell has a name. That name is one member from each stored dimension. So in Sample Basic, a number or an intersection doesn't have one part to its name. There are 5 dimensions, so it's got 5 parts to its name. One member name from each stored dimension. Everything we do in Essbase, we do based on intersection names. When we load data, we give it our, in the case of Sample Basic, 5 member names, one from each dimension, and that will tell Essbase where to load the data to. When we do queries, when we retrieve data, for example, in the Smart View, same thing. When we do calculations, same thing. An Essbase calculation cycles through every single stored cell unless we narrow the scope with an if or a fix or some other way of reducing the scope. Last, sparse calcs create blocks, dense calcs don't. Now, block creation is a bit more complex than that, but this is the key element of block creation that I found really very useful. So, how does that affect our design? Here's an abbreviated set of code. And this code calculates our units because units is on the left side of the equation, and it'll cycle through every member of every other dimension. So, for example, it's going to calculate all the months, it's going to calculate all the years, it's going to calculate all the products, etc. Except it's not going to calculate all the scenarios because scenario is in the fix. So the left side of this equation really isn't just units. The left side of this equation is really forecast units. Now this code is okay, but it's got 2 drawbacks. assuming a standard sample basic type of setup, accounts is dense. So this is a dense calc. It might not create blocks. Remember the simple stupid rule, sparse calc create blocks, dense calcs don't. And the other drawback is this only works on units, and it's hard-coded to only work on units. Now, here's a slightly different set of code. And if you notice, I've what I call pivoted the code so that forecast is now on the left side of the equation and units is in the fix. Now, this is exactly the same scope. It's exactly the same intersection. It doesn't matter whether it's forecast units or units forecast. So this calculates the same set of cells. But it's got one advantage. That is, it will create the blocks. It's got another advantage. We can just drop additional member names into the fix, and this calculation will work against many member names now. Now, by the way, is this slow because we're using a sparse calculation? It absolutely touches more blocks within the same scope. However, if you do this only on level 0, and one common best practice is to fix down on only level 0 blocks to do most of your calculation work, and then just ag what you need to ag. This isn't really slow because the ag is probably 80 or 90% of your calc anyway, so you're only doing 10 or 20% of your calc slower. So the advantage in block creation, I think, outweighs the any performance that you're going to lose. So the answer is not really. So we might want to convert this to an if, because we want to if on dense and fix on sparse for performance reasons. So this is just a technical conversion. It doesn't really make much difference in our design. It makes a difference in performance. And here's the same thing within the calc member block for the if statement. So let's talk about drivers on the view dimension. Take a look on the left side, and this is a picture of a driver-based budgeting application where the income statement items are in the accounts dimension. And then in order to get drivers for each of our income statement items, we'll add a driver to the accounts dimension. And that's fine, but we need to add, every time we add a new item to our income statement, we're going to need to add a second member to the accounts dimension for the driver. Then we're going to have to write a calculation line for that specific member. If we go over here to the right, we're going to see that so here's our view dimension with base, which is where we store most of our input, our dollars, and then another stored member for our drivers. If we add another member, let's say we just added miscellaneous, it's going to create space for both the dollars and the driver by adding one new member. And we only have to write one one calculation line, because that's going to apply to everything if that calculation is being done on a different dimension, in this case scenario. It's going to apply to all the other members on all the other dimensions. So by putting our drivers on the view dimension instead of the accounts dimension, we create something that's actually much simpler. It's got a lot fewer members on the accounts dimension and only one additional member on the scenario dimension. And it's much lower maintenance. So it's a nice, simple, elegant design. So, strengths of, if we put the drivers on the accounts dimension, we have one less dimension, but it's more maintenance and harder to write the code. If we put the drivers on the view dimension, it's easier maintenance, easier to write the code. We do have one more dimension, but if we've got a view dimension anyway, we really don't lose anything. And you could use other dimensions. You could do this on a version dimension, you could do this on a scenario dimension, but then you don't have the same level of flexibility. So let's take it one step further and add another forecast method. So here's the code we were looking at before, our percentage growth code. Let's add another method, and this is just going to be, so this is going to be the percentage growth. This is going to be a value times a driver. So for example, our cost of goods sold might be 40% of sales. So that's going to apply to cost of goods sold, payroll, and marketing. Each of them will have their own percentages that will be applied in a perfectly simple multiplication calculation. So what this is going to do is allow us to parameterize the method for sales and the method for COGS, payroll, and marketing, and allow the user to select which calculation method they want to use on each of these members. So, taking a look at all of the variables that we need and what type of prompts we want, the user is going to pick which business units, which products, which channels, which markets they want to forecast. The user is going to pick the years they want to forecast. The stored data members, things like view and HSP input value, the calculation designer is going to pick. What you want to put on the left side of the equation, in this case, forecast, the calculation designer is going to pick. We're going to have two calculation methods. The user is going to pick the accounts for method 1 and the accounts for method 2. So by the way, the V's are runtime prompts and the DTPs are design time prompts. The rest of these are outline identifications. So what's the name of your year dimension? What's the name of your periods dimension? What dimension has the drivers on it? And what member is the driver member on that dimension? So now that we've thought through the code and the variables that we need, what's the workflow for actually running this? First, we'll create the variables because as we go through the CDT, we're going to need those variables to be already created. We'll create the custom defined template. We'll drag in the a predefined script component with the rolling forecast code. We'll drag in member range components to create those additional outer fixes. We'll create the design time prompts. We'll create the steps and organize the steps and organize the design time prompts into the steps. Then in our code, we'll make substitutions for the runtime prompts and the design time prompts so that they're no longer hard-coded, so that they've got variables. So then we'll create the rule, and as we create the rule, we'll execute the CDT. When we drag it in, it will automatically execute. That is, when the rule designer drags it in, it will automatically execute, or we can execute it manually. We'll add some additional member ranges. Now, you could put all the additional member ranges into the CDT as well, but the member ranges are pretty easy to do. So, and I think it makes sense to keep the CDTs as small as possible and therefore as modular as possible. Now let's go back to a few slides from my January presentation because some of you may not have ever done a custom-defined template before, so you may want to see what some of the guts of that creation is. So I'm going to go through a handful of slides that takes us through the details there. So CDTs are like wizards. They're executed during rule development. We're going to drag in components. The components, this is a short list of the component types. The design time prompts prompt the designer of the rule for certain parameters. Steps are like pages in the wizard. CDT prompts are the questions that go into those pages. There are 3 built-in design time prompts: application type, application, and upper POV. The real useful one here is upper POV, but application type allows you to identify outlines that are project planning or public sector planning type outlines. The application allows you to identify a single or a multi-currency application. And so what upper POV does is it allows you to reduce the number of choices the rule designer will have to navigate, because it will eliminate, or you can set it up so that it eliminates all of the fixes that have already taken place in the script. So any outer fixes from where the upper POV DTP is can be eliminated. So it just simplifies the choices. So here are some of the choices you have to make in creating design time prompts. The type, there are 14 types, but we're going to focus on member range, member, and dimension. Dependency. So when I referred to the upper POV, if you make it exclusive of the other dimensions, then that's creating a dependency that will reduce the number of choices. And we'll see that in a minute. There are limits. You can cause the list of dimensions to include only certain categories. For example, you can say, will this prompt me only for the sparse dimensions or only for the dense dimensions? Will it prompt me only for the accounts dimension and possibly only the time dimension? In the case of planning, each of the required dimensions has a selection. So you can cause the prompt to provide each of those dimensions if you want to. Should it be prompted or should it be silent, essentially? Prompt it yes or no. Is it mandatory yes or no? Is it read-only yes or no? What will the text be? And what will it default to? So how do we create these design time prompts? So we select the design time prompt tab, the second tab here in our CDT template. We'll probably insert at the end. Here are 3 built-in design time prompts. So we'll insert a row at the end. We'll add the design time prompts. We'll go through fill out the form for each one. Second step will be, once we've created all of our design time prompts, we'll hit this button, and that's our pages button. We'll hit the plus to add a new page. We'll give it a name. We'll click OK. We'll then add whichever design time prompts to that step that we want, and input our time frame, input our data types. So they'll end up on the right. So here's using a DTP in a member range. So I've dragged in my percentage growth calc script here, and now I want to put my first fix on it. So I'll drag in the member range. Now, there's a couple of different things I could do. I could go down here and individually choose specific member names, or I could choose variables there. Now, in this case, I hit the variable selector button, which lets me do things that are a little bit fancier, and that has to do with the variable trick that I'll talk about at the end. But so this will let me pick variables from my DTP list. Now, notice in this case, it's populated both the HSP rates dimension with HSP input value and the view dimension, because I made a complex variable. I put both variable names in into this variable selection, and in one variable, and it populates both of them. Okay, so when I drag in my rolling forecast template, it will pop up the wizard pages. I'll make choices from the lists that I'm provided. So that will be the rule designer will be presented with that list. So here's the code after the CDT execution. You'll notice that this is all hard-coded. These things would be variables in the custom-defined template. Here's adding an additional member range for my business units and inner fix. Notice my VBUs is going to have 3 selections in it. So it'll populate all 3 of those dimensions. Add my data types slice. Okay, so that's the basic keystrokes. So in this case, we're going to drag in our, we'll go to System View, pick our application and database, right-click on templates, hit New, and then go down here within our application. In this case, within scripts, we're going to drag in the script that we wrote before that had the forecasting logic in it. We're going to substitute our design time prompts. So in that hard-coded script, in this, we could just type them in, but in this case, I've hit the replace button. So where I had forecast, I'm going to substitute DTP F forecast left side within square brackets. So that gives me about 5 substitutions. We'll do that with all of our variables. Here's our DTP for periods. Here's our DTP for years. We'll do the same thing with our runtime prompts. So we'll create the new rule. So this is the rule designer now. We'll create the new rule. They'll drag in the custom defined template. They'll go through the wizard execution. They may create additional member ranges, which are additional fixes. Save it and launch the rule. So here's the final rule fully expanded with both forecast methods. By fully expanded, I mean with the substitutions made with the variables in their final condition, not parameterized, hard-coded, but they remain parameterized in the script. We're just viewing it here in the final hard-coded view. And here's the final rule with the runtime prompts. So, for example, in the everything we see here in gray with the curly braces is the runtime prompts. Okay, so we'll go to questions. I've got a couple more slides that address 2 questions that came up at Kscope. So I'll just hit those first. If you want to chat any questions in, you can use the Q&A window, or you can use the chat window. In the meantime, while the questions are coming in, I'm going to hit just a couple of the questions that came up in at Kscope. How do you use this with ASO? So the workflow is really to create a new rule. You need a point of view object, and you need a formula object within the point of view object. Now, these are persistent calcs in ASO. Of course, we know that basically all calcs in ASO are dynamic. However, about 3 or 4 years ago, they introduced stored calcs in ASO, and you can do them without Calc Manager. It requires a MaxL script and what they call a calc script, but it's very different than a standard calc script. And it's, I believe it's kind of cumbersome to use. And doing this with Calc Manager makes it a lot easier. There's also one trick that I think is counterintuitive. It took me a long time to get it and we'll see what that is in a minute. So create a new rule, drag in a point of view object, drag in a formula object. So in the configure the point of view, click the left node of the point of view object. This is sample SAMP ASO. We have to go through every single dimension, and except in this case, I'm going to use the years for the formula. Every single dimension that isn't referenced in the formula needs to have an element in the point of view. Now, in regular Essbase BSO, you think if I leave it out of the calc, it will do that calc on every member of that dimension. So leaving it out of the calc is not only okay, but it's actually, the more you leave out, the more work it does. So we've all been trained to leave a lot of things out, to underspecify. It's exactly the opposite in these stored calcs in ASO. And that's the thing that took me a long time to get, because you have to go through every one of the dimensions and set up. In this case, I've just done a level 0 descendants on every one of the dimensions except for years. I'm going to use a calculation that's previous year equals current year. So all I'm doing is copying last year's data to this year. So here's what the formula will look like within my formula block. I'm just going to choose previous year equals current year, and that's all I need to do to create an ASO calc using Calc Manager. So what to watch out for, you've got to address every dimension. If it's not in the formula, if that dimension is not on the left side of the equation, it's going to have to be addressed by the POV. And by the way, you can't use any dynamic members in the POV. The variables trick, sometimes you can put variables within variables, and that will reduce the number of steps required. This is one of those don't try this at home tricks. It has worked for me just fine so far, but when I pointed this out to other people, they're skeptical that that's a supported behavior, and what that means is that it might disappear someday. So variables within variables do work at the moment, but they might not always. Let's see if we have any questions.